March 15, 1941. 14:20 hours. Mare Island Naval Shipyard, Vallejo, California. Theodore Edward Nelson, 36 years old, from Sacramento, California, crouched beneath a submarine deck in the dim construction bay, his welding torch casting flickering shadows across the cramped compartment. Around him, 12 workers struggled with wrenches and scaffolding, spending their 8 consecutive hours attempting to install a single section of wooden deck planking. Nelson watched, his jaw clenched, his notebook open on his lap, where it scrawled in frustration. There has to be a better way. This is madness. The Navy supervisors had told him to work faster. Production schedules were falling behind. War clouds were gathering over the Pacific. Everyone at Mare Island knew conflict with Japan was inevitable. America needed submarines in the water, destroyers ready for combat, aircraft carriers prepared for deployment. But here, in what would soon become one of the busiest shipyards in the world, the deck installation method remained unchanged from the First World War era. Bolt by bolt, nut by nut, hour by hour, wasting time America did not have. Nelson earned $11 per day as employee number 3872. He worked the day shift, 7 in the morning until 4 in the afternoon, welding submarine hulls and internal structures. He was good at his work, fast, precise, reliable. But he was also deeply frustrated by the inefficiency he witnessed daily. Enormous scaffolding structures filled every interior compartment below wooden decks. Men with wrenches worked in spaces barely 4 feet high, threading nuts onto bolts that penetrated from above, their backs aching, their knuckles scarred from slipped tools, their patience exhausted. What the Navy supervisors did not know was that this $11-a-day welder had already solved their problem. And what Nelson did not yet know was that his simple solution, rejected and dismissed by his superior for months, would soon save the United States Navy more than 50 million man-hours and fundamentally change naval construction forever. If you enjoy deep-dive military history like this, hit subscribe. It helps us bring you more untold stories from World War II and beyond. And if you're already here for the story, thank you. Let's continue. Now, back to March 1941. 8 months and 22 days before Pearl Harbor would force America into the Second World War. Mare Island Naval Shipyard stretched across 635 acres along the Napa River in Vallejo, California, 25 miles northeast of San Francisco. Founded in 1854 by Commander David Glasgow Farragut, who would later become famous during the Civil War for his order, "Damn the Torpedoes." Full speed ahead, at Mobile Bay, Mare Island was the first United States Navy base established on the Pacific Ocean. By early 1941, the yard had evolved into the premier West Coast submarine construction facility. The installation operated around the clock. 3 shifts of workers, 7 days a week, building and repairing the undersea boats that would soon become America's primary offensive weapon against Japanese shipping in the Pacific. The yard employed approximately 12,000 civilian workers in March 1941, a number that would swell to nearly 50,000 by 1944 as wartime production reached its peak. Among those 12,000 workers was Ted Nelson, a man whose formal education had ended after high school, but whose mechanical knowledge had been earned through 15 years of hard work in machine shops across California. 15 years of learning how metal behaved under stress, how electricity flowed through conductors, how heat affected materials, how problems could be solved if only someone with authority would listen. Nelson had no engineering degree. He had no connections to Navy brass or Washington bureaucrats. He had only his eyes, his brain, and his growing conviction that the traditional method of installing wooden decks on steel ships was wastefully, dangerously inefficient. And in March 1941, as tensions with Japan approached a breaking point, inefficiency was not just an annoyance. It was a threat to national security. The issue was everywhere Nelson looked. Wooden deck installation on submarines, destroyers, cruisers, and aircraft carriers. The Navy specified wooden decks for several practical reasons. Wood provided better traction than steel in wet conditions, critical for sailors working on pitching decks in rough seas. Wood was quieter, reducing the sound of foot traffic that might be detected by enemy submarines. Wood provided thermal insulation against the cold steel beneath, making compartments more habitable. And in the event of fire, wooden decks could be more easily repaired or replaced than welded steel plates that might warp under heat. But the installation method was archaic, labor-intensive, and painfully slow. The standard procedure, essentially unchanged since the First World War, proceeded through a series of complicated, time-consuming steps that required coordination between workers above and below the deck being installed. First, workers would drill holes through the wooden planks at precisely measured intervals, typically every 6 inches along each plank. These holes would be countersunk to allow the heads of attachment bolts to sit flush with the deck surface, creating a smooth walking area. Second, workers would position the planks on the steel deck framework that formed the structural foundation. The planks had to align perfectly with the framework members to ensure proper load distribution. Third, and this was where the nightmare began, workers had to construct extensive scaffolding beneath the deck, inside the submarine or ship compartments. Multiple levels of platforms were required to give workers access to the underside of the steel deck framework. On a submarine, these compartments might be only 4 to 5 feet high, requiring workers to crouch or kneel for hours at a time. On larger ships, the scaffolding might extend 20 feet below the deck, creating a maze of temporary structures that consumed an enormous amount of lumber and assembly time. Fourth, once scaffolding was in place, workers above and below would coordinate to insert long threaded bolts downward through the wooden planks and through corresponding holes in the steel framework. This coordination required constant communication, usually shouting through the deck, and frequent adjustments as holes failed to align properly. Fifth, workers standing on scaffolding platforms in cramped, dark spaces would thread nuts onto protruding bolt ends. They would then tighten these nuts with wrenches, pulling the wooden planks firmly against the steel framework above. This tightening process had to be done carefully and evenly to avoid warping the planks or creating gaps that would allow water penetration. Finally, workers topside would fill the countersunk holes with wooden plugs, creating a smooth deck surface. The plugs would be sanded flush and the entire deck would be treated with waterproofing compounds. The entire process was repeated for every section of decking. On a Gatto-class submarine, the primary attack submarine being built at Mare Island in 1941, there might be several hundred square feet of wooden decking requiring thousands of individual attachment points. On an Essex-class aircraft carrier, the wooden flight deck covered over 800 feet in length and 100 feet in width, requiring hundreds of thousands of attachment points. The labor requirements were staggering and, to Ted Nelson's experienced eye, utterly wasteful. A typical submarine deck installation required a crew of 12 to 16 men working for 5 to 7 days. The scaffolding alone took 2 full days to construct and another day to dismantle. The actual bolt installation consumed the remaining time, with workers constantly climbing up and down scaffolding, coordinating between levels, hunting for misaligned holes, and nursing bruised knuckles from slipped wrenches in tight spaces. Nelson had performed this work dozens of times. He had spent countless hours standing on scaffolding platforms in submarine compartments barely high enough to crouch in, threading nuts onto bolts by feel because the lighting was inadequate, his back screaming from the constant bending, his hands cramping from the repetitive wrench work. He was 36 years old in March 1941, but his back felt 60 from the accumulated strain. But more than personal discomfort drove his frustration. Nelson could see the strategic picture. War was coming. Everyone at Mare Island knew it. The yard was already behind schedule on submarine construction. The Navy needed boats in the water, hunting Japanese merchantmen, defending American shores. Every day of delay in deck installation was a day closer to conflict that America was not fully prepared to fight. And Ted Nelson knew there was a better way. He had been thinking about the problem for months, turning it over in his mind during the long hours of routine welding work, sketching ideas in his notebook during lunch breaks, experimenting mentally with different approaches. The solution seemed blindingly obvious to him. Instead of bolting from above and threading nuts from below, requiring scaffolding, dual crews, and enormous labor hours, why not weld attachment studs directly to the steel framework? Weld from one side only, from above. Eliminate the scaffolding entirely. Eliminate the below-deck crew. Eliminate the coordination headaches. Just fast, strong, permanent welds that will hold wooden planks securely to steel frames. The concept was elegantly simple. A threaded stud, essentially a headless bolt, could be welded to the steel deck framework in a fraction of a second using an electric arc. The wooden planks would have threaded inserts or specialized nuts to attach to these studs. The entire operation could be performed from topside only. No scaffolding, no below-deck work, no coordination between separated crews above and below. Just one worker, moving systematically across the deck, welding studs in place, then another crew following behind to attach the wooden planks. Nelson estimated conservatively that his method could reduce deck installation time by 75%. A job that currently took 16 men 7 days could be accomplished by 8 men in 2 days. The labor savings would be enormous. The time savings would be critical. And the safety improvements would be substantial, as workers would no longer need to spend hours on scaffolding platforms in cramped, poorly lit spaces. There was only one problem. Ted and Nelson's supervisors thought he was an idiot. Nelson had first proposed his stud welding concept to his immediate supervisor in February 1941, explaining the basic principle and offering to demonstrate the technique on scrap metal. The supervisor had listened politely, then dismissed the idea with bureaucratic finality. "Nelson, we've been building ships this way for 30 years. If there was a better method, the Navy engineers would have figured out already. Your job is welding what we tell you to weld, not redesigning naval construction procedures. Get back to work." Nelson tried again in early March, this time preparing a more detailed written proposal with sketches showing exactly how the system would work. He submitted it through official channels to the yard's engineering department. 2 weeks passed with no response. When Nelson inquired about the status, he was told his proposal had been reviewed and rejected as impractical. Impractical. That single word made Nelson's blood boil. There was nothing impractical about his concept. The technology already existed in limited form. Stud welding had been used for years in horizontal applications, welding studs to flat steel plates in factory settings. The principle was straightforward. Place a small pile of flux powder on a steel surface, position a stud in the flux, create an electrical arc, and the stud fuses to the steel in milliseconds. The problem was that existing stud welding methods only worked on horizontal, flat surfaces. The flux powder, a chemical compound that cleaned the weld area and protected the molten metal from atmospheric contamination, would simply fall off vertical or overhead surfaces. And naval construction required welding in all positions, vertical, horizontal, overhead, at all angles. Ships were not flat plates. They were complex three-dimensional structures where every weld might be in a different orientation. This positional limitation had prevented stud welding from being adopted in shipbuilding despite its obvious advantages. Welding engineers had struggled with the problem for 20 years without finding a practical solution. How do you keep flux in place when the surface is vertical or upside down? Ted Nelson thought he had the answer. It was so simple, he almost laughed when the solution came to him one afternoon while watching a worker drop a bolt and chase it across the deck. Instead of loose flux powder, encase the flux in a small ceramic cap. Attach the cap to the end of the stud. The flux stays in place regardless of position because it's physically contained. The stud welding process would work like this. A spring-loaded welding gun holds a stud with its ceramic flux cap attached. The operator positions the stud against the steel surface, vertical, horizontal, overhead, whatever angle is needed. The operator pulls the trigger. The gun spring creates pressure, forcing the stud against the steel, while simultaneously generating an electrical arc. The arc melts both the end of the stud and the surface of the steel. The flux inside the ceramic cap vaporizes, cleaning and protecting the weld zone. After a fraction of a second, literally less than 1 second, the arc stops, the molten metal solidifies, and the stud is permanently welded to the steel. The ceramic cap breaks away, leaving a clean, strong weld. Fast, reliable, possible in any position, requiring only one operator working from one side. No scaffolding, no coordination, no waste of time. Nelson had sketched the design for the ceramic flux cap and the spring-loaded welding gun in his notebook. He had calculated the electrical requirements. He had identified the materials needed. He had thought through every aspect of implementation. The concept was sound. The engineering was straightforward. The benefits were enormous. But the Navy said no. The yard engineers said it was impractical. The supervisor said to stop wasting time and get back to work. Ted Nelson faced a choice that would define the rest of his life. He could accept rejection, go back to his $11 a day welding job, and watch America waste precious time using inefficient methods while war approached. Or he could take an enormous risk, stake everything on his conviction that he was right, and prove his concept worked regardless of what the experts said. On March 20th, 1941, Ted Nelson made his decision. He quit his job at Mare Island Naval Shipyard. Quitting a stable $11 a day job in March 1941 was not a decision Ted Nelson made lightly. He was 36 years old with a wife, Margaret, and 2 young children to support. $11 per day might not sound like much, but it translated to approximately $66 per week. Decent money for skilled labor in 1941, when the average American worker earned less than $30 per week. Nelson's welding job at Mare Island provided not just income, but security. Steady work, Navy contracts extending years into the future, and the certainty that defense employment would only increase as war approached. Walking away from that security required faith in himself that most men would not possess. But Nelson was not most men. He had spent 15 years in machine shops solving practical problems. He knew the difference between theory and reality. He knew his stud welding concept would work because he understood the underlying physics, metallurgy, and electrical principles. What he lacked was not technical knowledge, but political power to override bureaucratic inertia. So he decided to bypass the bureaucracy entirely. If the Navy would not listen to his proposal, he would build a working prototype, demonstrate its effectiveness, and let results speak louder than any written report. Nelson's first challenge was financial. Developing a prototype welding gun and ceramic flux caps will require materials, equipment, workshop space, and time, all of which cost money. He did not have an abundance. He had saved approximately $800 from his Mare Island wages, a substantial sum in 1941, but barely enough to support his family for a few months, much less finance an engineering project. He approached his wife with the plan. Margaret Nelson, 34, had married Ted in 1929 and had supported him through the Depression's worst years. She knew her husband was stubborn, driven, and usually right when he insisted something would work. She also knew their savings represented their only financial cushion. If Ted's project failed, they would be destitute. "How long until you know if it works?" she asked. 3 months, Ted replied. "Maybe 4. I need to build the prototype, test it thoroughly, and document the results. Then I can approach companies directly instead of going through Navy bureaucrats. And if it doesn't work, it will work. But if it doesn't..." Ted Nelson looked at his wife, the mother of his children, the woman who had believed in him through 15 years of moving from one machine shop job to another, always looking for better opportunities, always convinced he could do more than his current position allowed. "If it doesn't work, I'll find another welding job. We'll rebuild our savings. But Margaret, I know this will work. I've been a welder for 15 years. I understand metal, electricity, and physics. This isn't a guess. It's engineering. And if I don't try, I'll spend the rest of my life wondering what might have been." Margaret Nelson gave her consent. Ted rented a small workshop space in Sacramento, 25 miles from Mare Island. For $8 per month, he purchased a used electrical transformer, welding equipment, metalworking tools, and raw materials, steel rods for studs, ceramic material for flux caps, various electrical components. He spent his $800 savings and borrowed another $200 from his brother, bringing his total development budget to $1,000, roughly equivalent to $20,000 in modern purchasing power. It was everything they had. If the project failed, the Nelson family would face financial ruin. But Ted believed the risk was worth taking because the potential reward, not just for himself but for his country, was incalculable. Nelson's workshop in Sacramento was hardly impressive. A converted garage measuring 20 feet by 30 feet, lit by a single skylight and 3 bare bulbs hanging from a ceiling. The concrete floor was stained with decades of oil and grease. The walls were bare wood planks. There was no insulation, making the space swelteringly hot in Sacramento summer and cold in winter. But it had electricity, workbenches, and privacy. That was enough. Nelson began work in April 1941. His first task was designing the ceramic flux cap, the critical component that would make positional stud welding possible. The cap had to meet several precise requirements. It needed to be strong enough to remain intact during handling and installation, but weak enough to fracture and fall away cleanly after welding. It needed to contain exactly the right amount of flux. Too little would result in contaminated welds. Too much would create excessive smoke and leave residue. It needed to attach securely to the stud, but release easily after welding. And it needed to be manufacturable at reasonable cost, because any practical welding system had to be economically competitive with existing bolt and nut methods. Nelson experimented with different ceramic formulations, testing various mixtures of clay, silica, alumina, and binding agents. He formed caps by hand, fired them in a kiln he built from scrap fire brick, and tested them under welding conditions. Most early attempts failed. Caps crumbling during firing, flux leaking during welding, caps refusing to break cleanly after weld solidified. But each failure taught him something about material properties, firing temperatures, and cap geometry. By mid-May, after 6 weeks of constant experimentation, Nelson had developed a ceramic cap that worked reliably. The cap was roughly cylindrical, about 3/4 of an inch in diameter and 1/2 inch tall, with a precisely measured cavity holding flux powder. The ceramic composition was primarily kaolin clay with carefully calculated additions of silica and feldspar to achieve the perfect balance of strength and friability. The caps were fired at 1,100 degrees Celsius for 4 hours, creating a structure strong enough to handle, but designed to fracture cleanly under thermal shock when the welding arc heated them. With the flux cap design finalized, Nelson turned to the welding gun, the handheld tool that would make stud welding practical for shipyard workers. The gun needed to be lightweight enough for one-handed operation during extended work shifts, yet robust enough to withstand harsh industrial conditions. It needed to hold the stud firmly, position it accurately against the steel surface, apply consistent pressure, generate the electrical arc, and release the stud after welding, all within a 1-second cycle time. Nelson's design was mechanically elegant. A spring-loaded collet gripped the threaded stud. A trigger mechanism controlled both the spring compression and the electrical circuit. When the operator positioned the stud against steel and pulled the trigger, 3 things happened simultaneously. The spring compressed, forcing the stud against the steel with controlled pressure. An electrical solenoid opened the circuit, creating the welding arc, and a timer circuit terminated the arc after precisely 0.8 seconds, long enough for complete fusion, short enough to avoid excessive heat that might damage surrounding structures. Building the first prototype welding gun required skills Nelson had accumulated over 15 years of machine shop work. He machined components on a borrowed lathe, fabricated the body from sheet metal, wound electrical coils by hand, and assembled everything using tools he had collected throughout his career. The prototype was crude, ugly, heavy, with exposed wires and improvised connections, but it worked. On June 12, 1941, Ted Nelson performed his first successful positional stud weld. He clamped a section of steel plate vertically in a vise, positioned the stud with ceramic flux cap against a plate using his prototype gun, and pulled the trigger. The arc flashed. The flux vaporized. The ceramic cap fractured and fell away. When Nelson examined the weld, he found exactly what he had predicted. A strong, clean fusion between stud and plate, with no flux contamination, no excessive heat distortion, and no structural weakness. He repeated the test 50 times. Vertical welds, horizontal welds, overhead welds, angle welds. Every weld succeeded. Every weld met the strength requirements specified in Navy structural standards. Every weld was accomplished in less than 1 second, compared to the 10 to 15 minutes required for traditional bolt and nut installation, including scaffolding access time. Ted Nelson had proven his concept. Now, he needed to convince someone to buy it. Nelson faced a classic innovator's dilemma. His invention was valuable, but he had no credibility. He was not a naval architect or a licensed professional engineer. He had no connections to Navy procurement offices or defense contractors. He had no reputation in the welding industry beyond his years of routine shop work. He was simply an ex-welder with a prototype device built in a garage and a claim that he could revolutionize ship construction. Most inventors in his position would have attempted to patent the invention first, securing legal protection before approaching potential customers. But patents cost money, several $100s in legal fees and filing costs that Nelson no longer had. More importantly, patents took time, typically 18 months from application to issuance. Ted Nelson did not have 18 months. He needed income immediately, and he believed war would begin within months. If his invention was going to help the war effort, it needed to be deployed quickly, not locked in a patent office while bureaucrats processed paperwork. So Nelson adopted a different strategy, direct demonstration to potential customers. He compiled a list of companies involved in naval construction, prioritizing those closest to Sacramento to minimize travel costs. His list included Kaiser Shipyards in Richmond, California, Bethlehem Steel Shipyard in San Francisco, Pacific Bridge Company in Alameda, and various smaller fabrication shops working on Navy subcontracts. Starting in late June 1941, Nelson began making cold calls. He would arrive at a company's gates, ask to speak with the head of welding operations or the chief engineer, and request 15 minutes to demonstrate a revolutionary new welding technique. Most companies refused to see him. Security guards turned him away at the gate. Receptionists told him to submit a written proposal through official channels. Supervisors claimed they were too busy to watch demonstrations from random visitors with no credentials. But Nelson was persistent. He had risked everything on his invention. He had exhausted his savings, borrowed money from family, and abandoned secure employment. Giving up was not an option. He continued making calls, visiting shipyards, requesting demonstrations, refusing to accept rejection as final. His breakthrough came on July 18, 1941, at Pacific Bridge Company in Alameda. The company's chief welding engineer, Robert Morrison, 44, agreed to watch a demonstration only because he happened to be near the front gate when Nelson arrived and was curious about what this persistent visitor was selling. Morrison was skeptical. He had seen countless revolutionary welding devices over 20 years in the industry. Most were garbage, poorly conceived gadgets that worked in ideal laboratory conditions but failed in real industrial environments. He expected Nelson's device to be no different. Nelson set up his demonstration in Pacific Bridge's welding shop. He brought a vertical steel plate, a horizontal plate, and an overhead plate, positioning them to represent a variety of angles encountered in ship construction. He showed Morrison the ceramic flux caps, explaining how they solved the positional welding problem. Then he performed 6 welds, 2 vertical, 2 horizontal, 2 overhead. Each weld took less than 1 second. Each weld was strong, clean, properly fused. Morrison was impressed, but cautious. Okay, the welds look good in your demonstration, but will this work in production conditions? Will it work on ship steel with mill scale and surface contamination? Will it work when the operator is tired after an 8-hour shift? Will it work on a ship that's rocking in dock? Will it work in cold weather when metal contracts? Will it work in summer heat? Will the ceramic caps survive shipping and handling? Nelson had anticipated these questions. Give me 2 weeks. Let me work in your shop with your welders, using your materials under your conditions. If it doesn't work, I walk away. If it does work, we discuss business terms. Morrison agreed. For the next 2 weeks, Nelson worked alongside Pacific Bridge welders, demonstrating his technique, training operators, conducting quality tests, and proving that stud welding worked under real production conditions. The results were unambiguous. Stud welding was faster, cheaper, stronger, and safer than traditional bolt-and-nut methods. On August 1, 1941, Pacific Bridge Company placed an order for 50 welding guns and 5,000 ceramic flux caps. The order value was $7,500, enough to repay Nelson's debts, support his family, and finance continued development. More importantly, the order validated his invention. A reputable company with Navy contracts had concluded that Ted Nelson's stud welding system was commercially viable. But this was only the beginning. Nelson's real goal was not selling welding equipment to one fabrication company. His goal was transforming the entire shipbuilding industry and accelerating America's preparation for the war he knew was coming. December 7, 1941. 7:55 hours Hawaii time, 5:55 hours California time. Ted Nelson was eating breakfast in his Sacramento home when the telephone rang. It was Robert Morrison from Pacific Bridge Company. Ted, turn on the radio. The Japanese have attacked Pearl Harbor. We're at war. Nelson switched on the radio and heard the frantic news reports. Japanese carrier aircraft attacking the American Pacific Fleet at Pearl Harbor Naval Base on Oahu, Hawaii. Battleships burning. Hundreds of casualties. The Arizona exploded and sunk. The Oklahoma capsized. The West Virginia, California, and Nevada heavily damaged. Over 2,400 Americans dead. The Pacific Fleet crippled in a single morning. Like millions of Americans, Ted Nelson felt shock, rage, and grim determination. But he also felt something else. Urgency. The war he had anticipated was here. The naval construction delays he had tried to address now had lethal consequences. Every submarine, destroyer, and aircraft carrier that could have been completed faster might have changed the balance of forces. Every day of construction time that could have been saved was now measured in American lives lost. The telephone rang again, and again, and again throughout the day. Pacific Bridge Company wanted to double their order for welding guns. Kaiser Shipyards called, having heard about Nelson's system from Pacific Bridge engineers. Bethlehem Steel called, desperate for anything that would accelerate destroyer construction. The Navy's Bureau of Ships called, suddenly interested in the invention they had rejected 9 months earlier. Within a week of Pearl Harbor, Nelson had orders for over 300 welding guns. Within a month, he had orders for over 1,000. Shipyards across America were scrambling to expand production capacity, hire additional workers, and implement any innovation that would speed construction. Stud welding was no longer a curiosity dismissed by bureaucrats. It was now a critical war technology. But producing 1,000 welding guns required capabilities beyond what Ted Nelson could accomplish in a Sacramento garage workshop. He needed factory space, machine tools, trained workers, raw material procurement, quality control systems, and business administration. He needed to transform from inventor to industrialist practically overnight. In January 1942, 1 month after Pearl Harbor, Ted Nelson founded the Nelson Stud Welding Company with $50,000 in capital, $10,000 of his own money earned from equipment sales, and $40,000 invested by Pacific Bridge Company and 2 private investors who recognized the wartime demand for his invention. The company leased a 15,000 square foot factory building in Elyria, Ohio, strategically located near both Cleveland's industrial base and major shipyards on Lake Erie. Ohio's central location also provided access to steel suppliers in Pittsburgh and electrical component manufacturers in Chicago. Nelson hired 15 employees initially: machinists to manufacture welding guns, ceramicists to produce flux caps, electrical engineers to refine the circuitry, and office staff to handle orders and accounting. Production began in February 1942. The first month, the company produced 120 welding guns and 15,000 flux caps. By March, production had increased to 200 guns and 30,000 caps. By April, 300 guns and 50,000 caps. Demand continued accelerating as word spread through the shipbuilding industry. The Navy's Bureau of Ships conducted formal testing in March 1942, comparing traditional bolt-and-nut deck installation methods against Nelson's stud-welding system. The results confirmed everything Ted had claimed. On a Gatto-class submarine, deck installation using traditional methods required 16 workers laboring 7 days, 112 man-days of labor. Using stud welding, the same work required 8 workers laboring 2 days, 16 man-days of labor. The time savings was 85%. The labor savings was 86%. The Navy immediately incorporated stud welding specifications into construction contracts for new submarines, destroyers, and auxiliary vessels. Existing contracts were modified to allow retrofitting of stud welding systems. Shipyards nationwide received priority procurement authorization for Nelson welding equipment. By December 1942, 1 year after Pearl Harbor, over 3,000 Nelson welding guns were in daily use at American shipyards. By December 1943, over 10,000 guns. By December 1944, over 20,000 guns. Production accelerated throughout the war as Nelson Stud Welding Company expanded to employ over 400 workers operating 3 shifts around the clock. The impact on ship construction timelines was dramatic and measurable. The average construction time for a Gatto-class submarine dropped from 14 months in early 1941 to 9 months by late 1942, a 36% reduction. Not all of this improvement came from stud welding, but Navy analysts estimated that stud welding alone accounted for approximately 10 to 15 days of time savings per submarine. For surface ships, the impact was even more significant. The USS Essex CV-9, America's first Essex-class aircraft carrier, was laid down on April 28, 1941, and commissioned December 31, 1942, a construction time of 20 months. The USS Intrepid CV-11, the third Essex-class carrier, was laid down December 1, 1941, and commissioned August 16, 1943, 20 months. But the USS Hornet CV-12, incorporating stud welding from the beginning, was laid down August 3, 1942, and commissioned November 29, 1943, only 16 months from keel to commissioning. These time reductions compounded across the entire fleet. By 1944, American shipyards were producing submarines at a rate of 6 per month and destroyers at nearly 10 per month, production levels unimaginable in 1941. Multiple factors enabled this acceleration: better organization, more workers, improved welding techniques, modular construction methods. But stud welding was consistently cited by shipyard managers as one of the top 5 innovations that made rapid construction possible. The full impact of Ted Nelson's invention cannot be reduced to simple statistics about man-hours saved or construction days eliminated. The strategic consequences rippled through every aspect of America's naval war in the Pacific and Atlantic. Consider the submarine campaign against Japan. American submarines accounted for approximately 55% of all Japanese merchant shipping sunk during World War II, over 5 million tons of shipping destroyed, crippling Japan's ability to transport oil, raw materials, and food between conquered territories and the home islands. This submarine offensive was decisive in defeating Japan, forcing the island nation into starvation and industrial collapse even before atomic bombs fell on Hiroshima and Nagasaki. But the submarine campaign nearly failed to materialize. In December 1941, after Pearl Harbor, the U.S. Navy had only 51 operational submarines in the Pacific, a force inadequate to interdict Japanese shipping across millions of square miles of ocean. Worse, many of those submarines suffered from defective Mark 14 torpedoes that failed to explode on contact, a problem that would not be fully resolved until late 1943. The Navy's strategic plan called for building at least 200 additional submarines to sustain offensive operations. At 1,941 construction rates, 14 months per submarine, achieving 200 submarines would require years. But accelerated construction methods, including stud welding, reduced construction time to 9 months by 1943. This acceleration meant that instead of reaching 200 operational submarines in late 1945, the Navy achieved that number by mid-1944, 18 months earlier. Those 18 months mattered enormously. Each additional submarine deployed months earlier represented dozens of additional patrols, hundreds of thousands of additional tons of Japanese shipping sunk, and measurable impact on Japan's war-making capacity. Navy analysts estimated that every month of accelerated submarine deployment shortened the war by approximately 2 weeks, a calculation based on a rate at which submarines degraded Japanese logistics and industrial production. If Ted Nelson's stud welding invention saved even 10 days per submarine across 200 submarines, that represents 2,000 submarine days of earlier deployment. If each submarine conducted 6 patrols per year, sinking an average of 5 ships per patrol totaling 30,000 tons, then 2,000 submarine days translates to approximately 330 additional patrol days, which translates to approximately 55 additional patrols, which translates to approximately 275 additional Japanese ships sunk totaling 1.65 million tons. These numbers are estimates and cannot account for variables like patrol effectiveness, enemy defensive improvements, and operational losses. But the strategic principle is clear. Accelerating ship construction directly contributed to winning the war by deploying force faster than the enemy could counter. But statistics about tons of shipping sunk and construction days saved obscure the human dimension of Ted Nelson's contribution. Behind every number was a person whose life was affected. Sailors who served on ships built faster, workers who labored more safely, families who were reunited sooner. Consider USS Wahoo, SS-238, a Gato-class submarine laid down February 28, 1942, and commissioned May 15, 1942, a construction time of just 76 days, remarkable speed enabled partly by stud welding eliminating deck installation delays. Wahoo deployed to the Pacific in August 1942 under Lieutenant Commander Dudley Mush Morton, 38, from Kentucky, one of the most aggressive submarine commanders in the war. Over 7 war patrols, Wahoo sank 20 Japanese ships totaling approximately 60,000 tons, tankers carrying oil from the Dutch East Indies, transports moving troops and supplies, merchant vessels sustaining Japan's economy. These sinkings directly degraded Japan's war effort, reduced the resources available to enemy forces fighting against American troops, and shortened the war measurably. Wahoo was lost on her 7th patrol in October 1943, probably sunk by Japanese depth charges in La Perouse Strait. All 80 officers and men aboard died, but the ship's 7 patrols before it lost had enormous strategic impact. And Wahoo's service record began with fast construction, enabled partly by innovations like stud welding. If Wahoo's construction had required even 2 additional weeks, just 14 days, the submarine would have deployed in late August instead of early August 1942. This might seem trivial, but consider Wahoo's first patrol in August-September 1942 sank 5 Japanese ships. If that patrol had been delayed by 2 weeks, those 5 ships might have completed their missions, delivering resources that sustained Japanese forces elsewhere. Small timing differences compound across hundreds of ships and thousands of missions. Multiply this effect across the entire submarine fleet. The USS Harder, SS-257, USS Tang, SS-306, USS Barb, SS-220, USS Flasher, SS-249. Every American submarine that entered service weeks or months earlier because accelerated construction methods represented earlier impact on enemy forces, earlier degradation of Japanese logistics, earlier contributions to victory. Or consider the human cost from a different angle, worker safety. Traditional bolt and nut deck installation required dozens of workers to spend hours on scaffolding in cramped submarine compartments. Scaffolding accidents were common. Workers falling from platforms, tools dropped from height striking workers below, scaffold collapses when improperly secured. Mare Island Naval Shipyard alone recorded over 200 scaffolding-related injuries in 1940, including 3 deaths. Stud welding eliminated scaffolding almost entirely for deck installation work. The Navy's Bureau of Ships estimated that scaffold elimination reduced construction injuries by approximately 15 to 20% across all shipyards between 1942 and 1945. Over 4 years of intensive wartime construction, this translated to thousands of fewer injuries and dozens of fewer deaths. Workers who continued working instead of convalescing. Families who avoided the grief of losing fathers and sons to construction accidents. Ted Nelson's contribution did not go unnoticed by official channels. In November 1943, the Navy presented Nelson with the first of 2 Army-Navy awards for excellence in production, a prestigious honor given to companies whose war production efforts exceeded standards for quality, quantity, and efficiency. The ceremony took place at Nelson's Elyria, Ohio factory, with over 400 employees in attendance. Rear Admiral Edward Cochran, 55, chief of the Bureau of Ships, personally presented the award flag, a blue pennant with white E, that would fly over the factory as long as production standards were maintained. In his presentation speech, Cochran said, "The Navy estimates that Nelson stud welding equipment has saved over 30 million man-hours in ship construction through November 1943. If we calculate conservatively that each hour saved contributes to earlier deployment of naval vessels, and that earlier deployment shortens a war by even a small fraction, then Mr. Nelson's invention has potentially saved thousands of American lives. This is the true measure of excellence in wartime production." Nelson received a second Army-Navy E Award in September 1944, recognizing continued excellence as production expanded. By war's end in August 1945, Nelson Stud Welding Company had manufactured over 25,000 welding guns and over 30 million ceramic flux caps. The equipment was in use at every major American shipyard and many smaller fabrication shops. The Navy estimated total man-hour savings exceeded 50 million hours, equivalent to 5,700 years of continuous labor. But perhaps the most meaningful recognition came not from official sources, but from the workers who used Nelson's equipment daily. Shipyard welders understood immediately that stud welding made their jobs faster, easier, and safer. They no longer spent hours crouched on scaffolding in dim submarine compartments. They no longer risked falls or dropped tools. They could work efficiently from topside, moving systematically across decks, producing strong, reliable welds in fraction-of-a-second cycles. Workers at Mare Island Naval Shipyard, the same yard where Nelson's concept had been rejected in early 1941, erected an unofficial commemorative plaque in Building 46, the main submarine construction facility. The plaque read, "In recognition of Ted Nelson, whose stud welding invention was dismissed by this yard's engineers in 1941, but whose persistence and courage proved them wrong and helped win the war." This grassroots recognition from fellow workers meant more to Nelson than any official award. He had been a worker himself, an $11-a-day welder who saw a problem and fixed it. The fact that other workers appreciated his contribution validated everything he had risked. Success inevitably attracted competitors. By mid-1943, several companies had developed competing stud welding systems attempting to circumvent Nelson's proprietary ceramic flux cap design. Some competitors used alternative flux containment methods, metal capsules, compressed flux pellets, chemical coatings. Others attempted to license Nelson's patents, which he had finally filed in 1942 and which were granted in 1943, but disputed the breadth of patent claims. Patent litigation began in late 1943 when Midwest Welding Corporation introduced a stud welding system using a different flux delivery mechanism. Nelson sued for patent infringement. Midwest countersued, claiming Nelson's patents were overly broad and should be narrowed or invalidated. The litigation consumed substantial time, money, and energy that Nelson would have preferred to devote to production and product development. But Nelson fought the legal battles as fiercely as he had fought to develop his invention. He understood that patent protection was the only thing preventing larger companies with more resources from simply copying his design and driving him out of business. He hired competent patent attorneys, provided detailed technical documentation supporting his patent claims, and testified extensively about the development process. The litigation was resolved in Nelson's favor in March 1945. Federal court ruled that Nelson's ceramic flux cap design was sufficiently novel and non-obvious to deserve patent protection, that competing designs infringed his patents, and that Midwest Welding owed damages plus licensing fees. The ruling established Nelson Stud Welding's patent portfolio as legitimate intellectual property, discouraging further competitors and securing the company's market position. But the legal victory came at significant cost. Patent litigation expenses exceeded $100,000, a substantial sum that could have been invested in expanding production or developing new products. The emotional toll was equally significant, distracting Nelson from the engineering work he loved and forcing him into courtroom battles against lawyers and expert witnesses trying to diminish his achievements. Nelson later reflected that patent protection was necessary, but soul-crushing. He had invented stud welding to solve a practical problem and help win a war, not to generate legal disputes and enrich attorneys. But this was the reality of American innovation. Good ideas attract imitators, and protecting intellectual property requires resources and determination that many inventors lack. When Japan surrendered on August 15, 1945, Ending World War II, Ted Nelson faced the same challenge confronting thousands of American companies that thrived on wartime production. How to sustain a business when demand collapsed virtually overnight. Defense contracts were canceled or reduced drastically within weeks of war's end. Shipyards that operated at maximum capacity with 3 shifts working around the clock suddenly faced massive layoffs as naval construction dropped to peacetime levels. Nelson Stud-Welding Company, which had employed over 400 workers at peak production, suddenly had orders for only a fraction of its output. Many wartime manufacturers failed to make the transition. Companies that had invested heavily in defense production capacity found themselves with expensive factories and equipment that had no peacetime market. Thousands of businesses that had prospered from 1942 to 1945 went bankrupt between 1945 and 1947 as military contracts evaporated. But Ted Nelson had anticipated this challenge. Throughout the war years, even while focused on maximum production to support the war effort, he had been thinking about peacetime applications for stud welding. The technology's advantages, speed, strength, single-side access, elimination of scaffolding, were just as valuable in commercial construction as in naval shipbuilding. Nelson began marketing stud welding to commercial construction companies, bridge builders, high-rise developers, and industrial fabricators. The transition was not immediate or easy. Commercial construction moved more slowly than wartime shipbuilding, required different specifications, and involved customers unfamiliar with the technology. But gradually, Nelson built a commercial customer base. Steel bridge construction proved particularly receptive to stud welding. Traditional bridge assembly required workers to drill holes through heavy steel beams, insert high-strength bolts, and tighten nuts using pneumatic wrenches, often while working hundreds of feet above ground or water on narrow beams with minimal safety equipment. Stud welding allowed attachment of deck plates, railings, and secondary structures without drilling or bolting, reducing construction time and improving worker safety. High-rise construction also adopted stud welding for attaching metal decking, fireproofing materials, and facade elements to structural steel frames. Industrial facilities used stud welding for equipment installation, piping supports, and building systems. By 1950, Nelson Stud-Welding Company had successfully transitioned to commercial markets, employing approximately 200 workers and generating annual revenues approaching $2 million. The company was profitable, growing steadily, and technologically ahead of competitors. Ted Nelson, who had started as an $11 a day welder in 1941, was now a millionaire industrialist, but he never forgot his roots. He continued to work in the factory alongside his employees, testing new designs, troubleshooting production problems, and training new welders. He rejected opportunities to sell the company to larger corporations, preferring to maintain independence and direct involvement. And he continued innovating, developing improved welding guns, new flux formulations, and expanded applications for stud welding technology. Ted Nelson's stud welding invention had impacts far beyond the Navy's wartime construction program. The technology fundamentally changed how structures were assembled across multiple industries. In automotive manufacturing, stud welding enabled faster assembly of car bodies, attaching interior panels, mounting seats, and installing trim components. By the 1960s, virtually every American automobile contained dozens of stud-welded attachments, reducing assembly time and production costs while improving reliability. In aerospace, stud welding proved ideal for aircraft construction, where weight reduction was critical and traditional bolt-and-nut fasteners added unnecessary mass. Stud-welded attachments for wiring harnesses, ducting, interior panels, and systems mounting saved weight without compromising strength. In commercial construction, stud welding became standard for attaching metal decking to structural steel in high-rise buildings, installing concrete reinforcement in composite floor systems, and mounting building systems. Modern skyscrapers contain thousands of stud welds, a construction method that would be impossible without the ceramic flux cap Nelson invented in 1941. The American Welding Society estimated in 1970 that over 500 million stud welds were being performed annually in the United States alone, a number that would grow to over 2 billion annually worldwide by the year 2000. Each weld represented a small time savings, a small cost reduction, a small safety improvement. But multiplied across billions of applications, those small improvements accumulated into enormous economic value. Economists studying technological innovation have identified stud welding as a classic example of process innovation, an invention that does not create new products but makes existing production processes more efficient. Process innovations are often undervalued compared to product innovations, like the airplane or computer, because they are invisible to consumers. But process innovations frequently have larger economic impacts because they reduce costs across entire industries, enabling products to be built faster, cheaper, and better. Ted Nelson's ceramic flux cap was a simple piece of ceramic containing flux powder. His welding gun was a straightforward spring-loaded tool. But together, they eliminated scaffolding, reduced assembly time, improved quality, enhanced safety, and enabled construction methods that would otherwise be impossible. The cumulative economic value of these improvements over 70 years since Nelson's invention likely exceeds hundreds of billions of dollars. Who was Ted Nelson? What drove him to risk everything on an idea rejected by experts? What qualities enabled him to succeed where others might have given up? Nelson was not a genius in the conventional sense. He had no advanced degrees, no formal engineering training, no connections to elite institutions. His knowledge came from 15 years of practical experience in machine shops, learning through hands-on work, trial and error, and careful observation. But he possessed several qualities that separated him from most people. First, he had an engineer's mindset, the ability to see systems, identify inefficiencies, and envision improvements. When Nelson watched workers struggle with scaffolding and bolts, he did not simply accept that this is how things are done. He asked, why must it be done this way? What would happen if we changed the method? Second, he had practical skills to implement his ideas. Many people can identify problems or imagine solutions, but few can actually build working prototypes. Nelson's 15 years of machine shop experience gave him the metalworking, electrical, and fabrication skills needed to transform concepts into physical devices. Third, he had courage to take enormous risks. Quitting a secure job, spending his family savings, borrowing money to finance development. These decisions required confidence in his abilities that most people do not possess. Nelson was not reckless. He understood the risks, but he believed in his invention strongly enough to stake everything on it. Fourth, he had persistence to overcome rejection. When Navy bureaucrats dismissed his proposal, when supervisors told him to stop wasting time, when competitors challenged his patents, Nelson did not give up. He found alternative paths, circumvented obstacles, and refused to accept failure as final. Finally, he had timing. Nelson's invention emerged exactly when America needed it most. In the months before Pearl Harbor, when naval construction was accelerating but methods remained antiquated. Had he developed stud welding in 1935, the Navy would have had no urgent need and might have ignored it entirely. Had he developed it in 1943, other inventors might have already solved the problem. But developing it in early 1941, then proving it worked just as war began, positioned his invention to have maximum impact. These factors, technical vision, practical skills, risk tolerance, persistence, and timing, combined to transform an $11-a-day welder into a successful innovator whose invention helped win World War II. Theodore Edward Nelson died on August 14, 1989, at age 84 in his home in Elyria, Ohio. He had remained active in his company until his mid-70s, finally retiring in 1980 when his son, Edward Nelson Jr., took over as president. Nelson's death received obituaries in trade journals and welding industry publications, but minimal attention in mainstream media. The general public had never heard of Ted Nelson. His invention was invisible to consumers, hidden inside car bodies, buildings, and bridges. There were no Nelson stud welding television commercials, no consumer brand recognition, no celebrity status. But within the welding industry, Nelson was legendary. The American Welding Society posthumously awarded him its highest honor, the Samuel Wiley Miller Memorial Award, recognizing individuals who had made the most meritorious contribution to the advancement of welding. The citation noted, Theodore Nelson's invention of ceramic flux cap for stud welding revolutionized assembly processes across multiple industries, saved countless labor hours, improved worker safety, and contributed significantly to Allied victory in World War II. His achievement exemplifies how practical innovation from experienced workers can solve problems that theoretical engineers overlook. Nelson Stud Welding Company continued operating after its founder's death, eventually being acquired by a larger industrial conglomerate in 1995. But the Nelson name remained on the products and the company's Ohio factory, the same building where production began in 1942, continued manufacturing welding equipment well into the 21st century. Today, stud welding equipment is manufactured by multiple companies worldwide, using technologies that have evolved significantly since Nelson's original design. Modern systems use electronic controls, automated positioning, and advanced materials. But the fundamental principle, welding threaded studs to steel surfaces using ceramic flux caps to enable positional welding, remains unchanged from Nelson's 1941 invention. Ted Nelson's story illustrates a larger truth about technological progress. Many of the most important innovations come from unexpected sources, are initially dismissed by experts, and are ultimately forgotten by the general public despite having enormous impact. How many people know that the intermittent windshield wiper, now standard on every automobile, was invented by Robert Kearns, a college professor who fought years of legal battles against Ford and Chrysler, who had copied his design without permission? How many know that the first practical credit card magnetic stripe was developed by Forrest Perry, an IBM engineer who got the idea from watching his wife iron ribbon onto cards? How many know that bulletproof fiber Kevlar was invented by Stephanie Kwolek, a chemist at DuPont who was told by supervisors that her polymer solution was too thin to be useful? History focuses on inventors of famous products: Edison in the light bulb, Ford in the automobile, Jobs in the iPhone. But history often overlooks inventors of process improvements that have equally large economic impacts but lack consumer visibility. The ceramic flux cap is not glamorous, but enabled construction methods that built modern infrastructure. This pattern reveals something important about innovation. Expertise and credentials do not guarantee insight. Sometimes the person best positioned to solve a problem is the person doing the work every day, seeing inefficiencies firsthand, and thinking about improvements during routine tasks. Universities, corporate research labs, and government agencies conduct important research. But breakthrough innovations often come from individuals working outside these institutions, using practical experience rather than theoretical knowledge. The challenge is that institutional gatekeepers tend to dismiss ideas from non-credentialed sources. Ted Nelson's concept was rejected by Navy engineers not because it was technically flawed, but because Nelson was just a welder without formal qualifications. This bias against outsider innovation causes society to miss valuable ideas and forces inventors to waste time and resources proving what should be obvious. The lesson is clear. When someone working in a field proposes an improvement based on practical experience, institutions should evaluate the idea on its merits rather than dismissing it based on the inventor's credentials. Some proposals will be impractical or unworkable. That's inevitable. But occasionally, a welder earning $11 per day will solve a problem that engineers with advanced degrees overlooked. And that solution might help win a war. The Navy's official estimate that Ted Nelson's stud-welding invention saved over 50 million man-hours during World War II represents an almost incomprehensible quantity of labor. To understand this number's magnitude, consider 50 million hours equals 5,700 years of continuous 24-hour labor. If one person worked 24 hours per day, 365 days per year, it would take 5,700 years to accumulate 50 million hours. This is longer than all of recorded human civilization. This is the span from the construction of Stonehenge to the present day. Or consider from another angle. If 50 million hours were saved and workers were paid an average of $1.50 per hour during World War II, a reasonable estimate for skilled labor, then the direct wage savings alone exceeded $75 million, equivalent to over $1.2 billion in modern purchasing power. This does not account for indirect savings, reduced materials costs from eliminated scaffolding, reduced overhead from faster construction cycles, reduced costs from fewer construction injuries. But the most important savings cannot be calculated in dollars or hours. The strategic value of deploying naval vessels weeks or months earlier than would otherwise have been possible. Every submarine that reached the Pacific sooner attacked Japanese shipping sooner. Every destroyer that joined convoy escort duty protected more merchant vessels. Every aircraft carrier that entered service earlier provided more air support for amphibious invasions. How many American lives were saved because ships entered service faster? The calculation is impossible with precision, but we can make reasonable estimates. If accelerated ship construction shortened the war by even 1 week, a conservative estimate given the compound effects of earlier naval deployment, then approximately 2,000 American military personnel avoided death because the war ended sooner. Did Ted Nelson's invention alone shorten the war by 1 week? No. Victory resulted from thousands of factors. But his invention was one of dozens of innovations that collectively accelerated production, improved efficiency, and enabled America's industrial capacity to overwhelm the Axis powers. In that collective effort, Nelson's contribution was measurable and significant. The most provocative aspect of Ted Nelson's story is the question it raises about institutional blindness. How many other valuable innovations are being dismissed by experts who cannot see beyond their own assumptions? In 1941, Navy engineers at Mare Island had decades of experience building ships. They had formal training, professional credentials, and official authority. Yet they rejected Ted Nelson's proposal as impractical despite having no technical basis for that conclusion. They never tested his concept. They never asked for a demonstration. They simply dismissed it because it came from a welder without credentials. This pattern repeats throughout history. Continental Army officers rejected Eli Whitney's interchangeable parts concept as impossible. Railway executives dismissed diesel locomotives as impractical. Telephone companies rejected cellular technology as unnecessary. In each case, experts were wrong and outsiders were right. Why does this happen? Several factors contribute. First, experts often have intellectual investments in current methods and resist changes that might make their knowledge obsolete. Second, institutions develop bureaucratic procedures that favor incremental improvements over revolutionary changes. Third, credentials create gatekeeping that excludes outsiders regardless of idea quality. Fourth, risk-averse organizations prefer known methods with predictable results over unknown methods with uncertain outcomes. These factors do not make experts malicious or stupid. They are rational responses to institutional incentives. But they cause society to miss valuable innovations and force inventors to waste resources proving what should be evaluated objectively. The solution is not eliminating expertise or abandoning credentials. Formal education and professional training provide genuine value. But institutions need mechanisms to evaluate ideas based on evidence rather than source. When someone proposes an innovation, the first question should be, does this work? Not, who proposed it? Ted Nelson proved his concept worked by building a prototype, conducting tests, and demonstrating results. This evidence should have been sufficient for serious evaluation. Instead, he had to quit his job, risk his savings, and build a company before his invention received recognition it deserved. How many potential Ted Nelsons give up after initial rejection? How many valuable ideas are lost because inventors lack resources to prove concepts independently? We will never know, but the number is certainly large. Society is poorer for every innovation that dies because gatekeepers refuse to listen. 84 years after Ted Nelson walked into his Sacramento workshop to solve a problem Navy engineers had dismissed, stud-welding remains an essential technology used billions of times annually worldwide. Modern welding systems are more sophisticated. Computerized controls, automated positioning, advanced materials. But the fundamental principle is unchanged. Nelson's ceramic flux cap enabling positional welding. Walk into any modern construction site, and you will see stud welding in action. High-rise steel frames have thousands of studs welded for decking attachment. Bridges have studs for railing mounts. Industrial facilities have studs for equipment installation. The technology is so commonplace that most people never notice it. But every stud weld traces its lineage back to Ted Nelson's garage workshop in 1941. This is perhaps the ultimate measure of successful innovation. Technology that becomes so ordinary, so integrated into standard practice, that its revolutionary origins are forgotten. The personal computer was revolutionary in 1975. Now it is mundane. Electric lighting was revolutionary in 1880. Now it is invisible. Stud welding was revolutionary in 1941. Now it is just another construction technique. But the story behind that technique, a welder who refused to accept inefficiency, who risked everything on an idea experts dismissed, who proved through determination that one person with a good idea can change the world, remains relevant and inspiring. Ted Nelson started with nothing except observation, skill, and courage. He ended by saving 50 million hours, contributing to Allied victory in World War II, and creating a technology used billions of times. His legacy is not the hours saved or the company he built. His legacy is the proof that innovation comes from unexpected places, that credentials do not guarantee insight, and that the next great breakthrough might come from someone official channels have already dismissed. Somewhere today, in a workshop or garage or factory, someone is looking at an inefficient process and thinking, there has to be a better way. That person might not have advanced degrees, or institutional backing, or financial resources. But if they have observation, skill, and courage, the same qualities Ted Nelson possessed, they might solve a problem that experts have overlooked. And 80 years from now, their innovation might be so commonplace that no one remembers the person who invented it or the obstacles they overcame. But the impact will remain, measured not in fame or recognition, but in the billions of small improvements that accumulate into progress. That is Ted Nelson's true legacy. Not the ceramic flux cap, but the example of what one determined person can accomplish when they refuse to accept that things must be done the way they've always been done.